Okay, let's talk about equivalence relations. Now, equivalence relations are in some sense similar to functions, but not quite the same thing. Remember that we said that you can represent functions as a set of ordered pairs. And that's also true for equivalence relations. Okay. Remember, the set of ordered pairs, set of all possible ordered pairs, is A cross B. If the first element of the pair is in set A, second element of the pair is in set B, then the set of all ordered pairs is A cross B. All right, so we'll see that equivalence relations are also a subset of A cross B. However, equivalence relations have a different function. Function means you basically go from one thing to another thing. Equivalence relation means you're relating several things together. So they have a different purpose, but we'll see they have a very intricate relation. All right, now for example, the function mother could be represented as a set of ordered pairs, where the first element of the pair is the person and the second element is the mother. Now notice a very special thing about this set of ordered pairs. You say you have no two ordered pairs have the same first element. Okay? Because one person doesn't have two mothers. We're using the sense of biological mother. So you can't have Alice Cooper and Josephine and Alice Cooper and Georgiana. That's not possible. Unless there are two different Alice Coopers, in which case you need to specify the name more exactly. But you can't have two different individuals in A that have this, I'm sorry, you can't have one individual having two different biological mothers. That's not possible. All right, let's not talk about artificial insemination. But ordinarily, one person can't have two different mothers. Okay. Now that situation is not the same for a relation like this. If you have a person and a son. Now one person could have many sons. If I list this set of ordered pairs, I could have, I could have George H.W. and George W. And I can have George H.W. and Jeb. Okay. So these are two ordered pairs. George H.W. is the father of George W. So George W. is the son of George H.W. and Jeb is the son of George H.W. So I have two different ordered pairs where the first entry is the same. So this couldn't possibly be a function. However, it does indicate a useful relationship. So you can see that this kind of relationship might be something that you would want to characterize mathematically. Okay, and there are many, many cases of things like this. For instance, x is a sister of y. You couldn't characterize that as a function because y can have many sisters. X knew y in high school. Y knew many people in high school. Okay, so none of these examples could be related to a function. So this motivates us to make a more general definition. Suppose A and B are sets. Any subset of A cross B is called a relation from A to B. So any set of ordered pairs, first entries from A, second entries from B, that's called a relation. Okay. In this special case where the first and the second set are the same, we call this a binary relation. Binary because it's basically relating two elements from the same set. All right, now, here's some examples of relations that are not binary relations. But you see that every relation is a set of ordered pairs. Okay. Now the empty set is a set, so this is a bona fide relation. Okay. You also see that in this case you have a relation where we have 1, 4, 1, 5, 1, 6. That couldn't possibly be a function, but that is a bona fide relation. Okay. Also notice here that one empty set is not a relation because empty set is not an element. So be careful about that. All right, here's one relation that's a subset of another relation. If I consider all capitals of all states and say take the set xy where x is the capital and y is the state, so I'd have 50 elements in this relation, and here are 3 of them. So I have the second relationship contains the other. The first relation is a subset of the second. Okay, you'll find out that there are many, many relations. So this exercise is to explore the properties of relations. Now, as we've seen with functions, it's useful to have different ways of representing things. So you can actually represent a relation with an arrow diagram as follows. First, you draw a dot for each element of A. So you emphasize that this is a representation of a binary relation. You draw a dot for each element of A. And for two elements of A, you draw an arrow from A to B if AB is in the relation. Okay, so let's look at this particular example. Okay, we have this 5-element set, 1, 2, 3, 4, 5, and we say that x comma y is in the relation if x is not equal to y, and x squared plus y is less than or equal to 10. So let's consider some elements of the relation. All right, suppose x is 1. If x is 1, as long as y is less than 9, then xy will be in the relation. So 1, 2 is in the relation. 1, 1's not in the relation because they can't be equal. 1, 3 is in the relation. 1, 4 is in the relation. And 1, 5 is in the relation. Okay. If we let's do this systematically and think of all the things that all the elements that have 2 in the first component. So 2 squared is 4. So I can have 2, 1, that works. I could have 2, 2, that works. Let's see if 2, 3 works. You'd have 4 plus 3, that's 7, that's good. 2, 3 works. And 2, 5 works. And 2, 4 works, that works. All the way up to 2, 5. Those all work. Okay? Because here we have 4 plus 5 is 9, less than or equal to 10. All right, let's consider the ones with 3. All right, 3 is 3 squared plus 1, that makes 10. All right, none of the others work. Okay? And if I do 4, nothing. 4 is not related to anything. Okay, so this is the set of pairs in my relation. So if I draw the digraph, for instance, 1, 2, 1, 3, 1, 4, 1, 5. So notice if I'm going to draw arrows from each thing that's related, I have an arrow from 1 to 2, from 1 to 3, from 1 to 4, and from 1 to 5. We also found that 2 was related to everything, so I have an arrow from 2 to 1, 2 to 3, 2 to 4, 2 to 5. We found out that 3 was only related to 1, so there's an arrow from 3 to 1. Okay, so notice these two directional arrows indicating there's an arrow from 1 to 2 and from 2 to 1. Okay, so this is all the arrows. This encodes all the information of that binary relation. Okay, and here's some exercises give you a chance to do the same thing. Okay, now we're familiar with mathematical relations such as equals, less than, contained in. So we think of these as relations. We can actually connect this concept with the concept of relation that we've been talking about. We can represent equals as a set of pairs. Okay, and we can say the relation equal is represented by the set of pairs x, y such that x is equal to y. Here's a specific example. We can represent the relation less than as the set of ordered pairs x, y in R cross R such that x is less than y. Okay, so you have an ordered pair in this set if and only if x is less than y. Okay, so two different ways of writing the same thing. No new concept, just different notation. Okay, so this makes it easier to write. Instead of writing relation in this way, we can simply use the symbol itself. All right, sometimes we just want to talk about a non-specific relation, and we use this symbol tilde, or some people call it twiddle. So x tilde y means that x and y are related by the specific relation we're talking about. Okay, so let's consider some properties of relations. So now we're going to use this notation instead of this ordered pair notation. This is somewhat more compact and easier to use. Okay, so suppose that we have a binary relation on a set. There are three important properties that that binary relation can have. Now remember, in this case, in the relation, these are ordered pairs. Both the first and the second element are from A, and we could represent this by an arrow diagram. Now, a relation is reflexive if for every element in the set A is related to itself. And you'll explore what that means in terms of arrow diagrams. That's a useful exercise. We say that the relation is symmetric if and only if whenever A is related to B, then B is always related to A. Now that doesn't mean that A is always related to B for every B, but it says whenever A is related to B, in other words, whenever there's an arrow from A to B, there's also an arrow from B to A. Okay, so let's look back and see if in our previous example of arrow diagram, is this graph reflexive? Now, I said that reflexive means that every element is always related to itself. So is this graph reflexive? Well, I won't tell you the answer, but I want you to think about it. But I will say something that you consider this arrow. Okay, this arrow is missing from the diagram. That tells you something. Now, is this, so that's one thing. Is this diagram symmetric? Well, consider 4 and 3. Okay. Now, what symmetric means is that if 3 is related to 4, then 4 must be related to 3. So, in fact, in this case, neither is related to neither, so it doesn't tell us anything about whether the relation is symmetric or not. This does not disprove symmetric. Okay. In this case, we have 1 and 2. 1 is related to 2, and 2 is related to 1. Okay. So that seems to confirm symmetric. However, look at this. 1 is related to 5. 5 is not related to 1. Okay, so this shows that in fact the relation is not symmetric. If the symmetry relation holds for any pair in the graph, the relation is not symmetric. All right, the last property is transitive, and we say that the relation is transitive if whenever A is related to B and B is related to C, then A is related to C. So let's see how that works for our diagram up here. All right, consider 2, 4, and 3. Okay, 2, 4, and 3. So what this is saying is that the transitive says if 2 is related to 4 and 4 is related to 3, then 2 must be related to 3. Okay. So does this disprove or prove transitivity? Actually, this doesn't say anything about transitivity because 2 is related to 4, but 4 is not related to 3. Okay. Let's write down some other examples and see how this works. Okay. Remember, transitivity in general means like this. A is related to B, and B is related to C, implies A is related to C. All right, so let's see how let's do A, B, and C, and see if we'll do some checks here. And we'll see, so does it hold? Okay. So let's consider 5, 4, and 3. Okay. Now in this case, 5 is not related to 4. 4 is not related to 3. Okay. So the hypotheses here do not hold. All right. So this condition is not violated. Okay. So this is okay. Okay. What you have to check is whenever these two conditions hold, then this condition has to hold. For instance, let's consider 1, 2, 5. Let's consider that. 1 is related to 2, 2 is related to 5, and 1 is related to 5. This is okay. Okay. Let's consider 2, 4, 5. Okay. 2 is related to 4. 4 is not related to 5. These hypotheses do not hold. B related to C does not hold. So this is okay. Okay. You only get a violation if you have these two both holding and this one not holding. In fact, you can go and check all these relations and you'll find, in fact, that this relation is transitive. Now let me give you an example. If we added two arrows, if I added this arrow and this arrow, if I added those two arrows, and you considered 5, 4, and 3. Now look, 5 is related to 4, 4 is related to 3, 5 is not related to 3. So this is not okay. But that's only true if I add these two relationships. Okay. So if you have Transitive, failing, it means you can find two arrows such that the third arrow does not exist. Two successive arrows such that the direct arrow does not exist. Okay. All right, so here's some examples of relations that you show explicitly when they're reflexive or not. Okay, that's reflexive, symmetric, and transitive. Okay, so you get several exercises. You can do that also with a another arrow diagram. Okay, and some more examples, many examples of this. Okay. Okay, so let's look at some properties of equivalence relations. Now, equivalence relations are useful for classifying. Okay, you see that this says equivalence. You're looking for things that in some sense are the same. So this example, say for instance, we classify animals according to species. We say X is related to Y if X and Y are the same species. Now, if you think about the three properties, you'll discover that that reflexive, symmetric, and transitive do hold for this relation. So the discussion is down here. Here's another example of equivalence relation. You classify people according to their first name. So we define this equivalence relation. X is equivalent to Y if and only if X has the same first name as Y. Go ahead and verify that the three properties hold: reflexive, symmetric, and transitive. Now here you do a congruency in geometry. In this case also the three properties hold. Okay. So we define formally an equivalence relation on a set A as a binary relation. Remember, that's a subset of A cross A. That's reflexive, symmetric, and transitive. Okay, more examples of binary relations. Now this one's a little confusing. This is a binary relation on pairs of numbers. Okay, it's a binary relation on pairs of numbers. So this binary relation is a subset of n cross n cross n cross n. Okay, so be careful here. When you're trying to show symmetric, for instance, it has nothing to do with A1, B1 is related to B1, A1. Has nothing to do with that. Okay. Symmetric means if A1, B1 is related to A2, B2, then A2, B2 is related to A1, B1. So be careful about that. This is a relation on pairs of numbers. Okay, so make sure that you apply the definitions exactly. Okay, so here's some more examples of binary relations that you can try out. Now, actually, we've been talking about equivalence relations. We say that they're some sense similar to functions. In fact, we can derive equivalence relations from functions. Right? So let's see how this works. Species is a function on animals. So the equivalence relation same species can be defined in this way, that X is equivalent to Y if and only if the species of X is equal to the species of Y. Okay? So there's a diagram here. If I take all animals here, and I take the species function here, and then here's the set of all species. So for instance, we have here dogs or whatever. I don't know the... Okay. And then you have several different animals here, several different types of animals that are dogs, that all map to dogs here. Okay. All of these points map to the same point D here. And then we take this set that consists of all the points in animals, all the animals that map to dogs. Okay? And we say that any two of these are equivalent. Any two animals that both map to dogs are the same species. Okay, and we can do that with others. You have cat down here. Of course, they're not going to be, those are going to be disjoint. So we have cats all going here. Okay, so down here is the set of of cats. I know as I said, I don't know dogs and cats are not species, but I think you get the idea. Okay? So we say all of these cats are equivalent to each other. Okay? You can do the same thing with other examples too. So you can use a function to define a binary relation. And you define the binary relation on the domain. Okay? The binary relation is defined on the domain. Okay? All right. Now notice in this case here, when we were talking about dogs, we had a set here where any two elements in this set are equivalent. Doesn't matter where they are. In this subset of dogs, any two elements are equivalent. This is actually what you'd call a complete graph. Any relation holds in this set of points. Okay. So we basically have divided the set of animals up into classes. And that's where the notion of equivalence class comes from. Okay. Here's the definition. If we have an element of A, the equivalence class is the set of all other elements of A that are equivalent. Okay, so remember that picture that I drew above. Here's one dog. I can take all dogs that are equivalent to this one. Here's one cat. I can take all cats that are equivalent to that one. These are two different equivalence classes. Okay, so for every equivalence relation, you can define a set of equivalence classes. All right, now pay attention to this warning. The notation square brackets A, that is the equivalence class that contains A, does not tell us which equivalence relation is being used. You should be able to figure out which relations from the context. So we'll only use this notation when we're making clear what relation we're talking about. All right, so here's an example of a set A, and here's an example of a relation defined as a set of ordered pairs. You could draw a graph to represent this. And let's consider the equivalence classes. First, we need to find everything that is related to 1. Well, 1 is related to 1, 3, and 4. Okay? If you do 2, you can see that 2 is related to 2 and 5. What about 3? Well, 3 is related to 1, 3, and 4 as well. Notice that these two classes are the same. And it's also the same as 4. So for any element in the class, it gives me the same class. Same with this case. 2 and 5 are in the same class. So 2 and 5 is the class of 2, and it's also the class of 5. So really, I only have two distinct classes, and the two distinct classes are actually disjoint. All right, and that's actually expressed here. Any element is in its own equivalence class. So that means the equivalence class of any element is non-empty. The union of all equivalence classes is the entire set. Any two elements that are related have the same equivalence class. Any two elements that have different are not related have different disjoint equivalence classes. There's no overlap. Okay, very important property. Okay. All right, we'll stop there and finish the rest in the next video.